Okay, welcome back to Genevieve's third and final talk on L2 homology and boundaries.
Okay, so today I'm going to try to relate the things I was talking about the last two times. I'll just say the previous things related. I'll be mainly talking about L2 homology and incoherence. So the key, let me talk about L2. The key motivator connection between L2 homology and geometric group theory is this result, which was in Gromov's paper on asymptotic invariance of infinite groups, and also really written out for discrete groups in a paper of Pansu. So all my groups are going to be of finite type, and I'll even be assuming that I have a finite k pi 1. So I won't write that every time. If G and G prime are quasi-isometric, then the L2, right, Bn2 of G is equal to Bn2 I'll write this. G is equal to 0 if and only if Bn2 of G prime is equal to 0. So in other words, the vanishing of L2 homology. So remember that this dimension is going to be 0 exactly when the actual homology space is trivial. Okay, so the vanishing of L2 homology is a QI invariant. Okay, and another fact that's very useful and related to a lot of techniques that are used both in geometric group theory and in geometric topology is looking at finite index covers. Or finite index subgroups. Okay. So, definition. So I have G, a finitely generated group, and a residual chain Gn and containing N is a nested sequence so I have a G, and then I'll have a subgroup. These are all going to be normal, such that each GI is normal in G, and the intersection of the GI equals the identity. Okay, so if you can keep taking, I think of this as taking covers on and on and all the way up to the universal cover. Okay, so a group is residually finite. It admits a residual chain. Okay, so Luke's approximation theorem is Luke's finite index, thank you. And finite index, thank you. Put little dots here. Okay, so keep taking. Okay, and then I wanted to make a comment here. There exists, so you might think this is a normal situation if you're like looking at hyperbolic 3 manifolds. So alert. Okay, there exists finitely presented infinite simple groups. Even nice groups that act on heads or cube complexes, these act on a product of trees. So this is a non-trivial condition. Okay, so now I have X is a connected CW complex of finite type. With residually finite fundamental group. Pi1 of X equal to G. Okay, and I'm going to have Gn going to be a residual chain. And I'm going to let Xn be the covers corresponding to Gn. So that pi1 of Xn, so these are covers of X corresponding to the subgroups Gn. So pi1 of Xn equals Gn. Okay, then the L2 Betty numbers of X are going to be equal to the limit as n goes to infinity. Okay, so now this looks the same, but this is actually, I don't have a 2 here, so these are the regular Betty numbers. So I can take homology with like real coefficients, okay, and get these, the rank of that, divided by the index of G and G. Okay, so this L2 Betty number that's telling you the action of the fundamental group on the universal cover can be seen by looking at a sequence of covers and just the regular old Betty numbers of the sequence of covers going to infinity, which is a really nice result. Okay. All right. BK of Xn just equals the rank of, say, H1 of Xn Q. Okay, so let's look at what this can tell us about as examples. So for example, let's look at a fibered 3 manifold, and this will hold for, in general, something that's a fibered group. Let's just do a fibered 3 manifold since we saw this earlier. Okay, so I have, oh yeah, thank you. Keep doing that today, I'm tired. Thank you. Okay, so pi1 of M3, in this case, is going to map to Z. Okay, the kernel is going to be a surface. And I have this fibered 3 manifold, as we saw yesterday. I can take it by form, I can make a model of this fundamental group by taking a surface times the identity and then gluing the top to the bottom. If I want it to be hyperbolic, I'll make it be a pseudo-Nosov remorphism. Okay, and then I can further map this to, say, Z mod NZ. And the composition of these, the kernel would give me a normal subgroup, which is just an n-fold cover. So if it was a 2-fold cover, it would become like this. I have another copy here. Instead of gluing by phi, I'd be gluing by phi squared. This was a 2 to the 2z. And I can keep doing this. And I can also get the, so because of this limiting procedure here, we can see that, so the Luke's theorem is going to tell us that the first L2 Betty number, so Notice that the Betty numbers of these are going to be bounded. The regular Betty numbers of these manifolds are going to be bounded because the surface with this sequence of covers, I'll have to take another sequence of covers to get up to the whole universal cover. So with this like subsequence of covers, the Betty number is going to be bounded. Okay, so the Betty number of this is going to be bounded, but the index is going to be going to infinity. Okay, so the B2 of this pi1 of M3 is equal to 0. Okay, as we keep going up. All right, so that's nice, and that's general and true for a fibered manifold, as we'll see. Okay, so free bicyclic groups are L2 acyclic. Okay, so the first L2 Betty number of G, where G is free bicyclic, okay, is equal to the 0th is equal to 0 just because it's infinite. The first one is going to be equal to 0 because it's fibered, and then the latter ones are going to be equal to 0. The second one's going to be equal to 0 because of the Euler characteristic. So remember, the sum of the Betty numbers equals the Euler characteristic. So this is because it's infinite. This is because it's fibered. And this is because the Euler characteristic of a free bicyclic group is equal to 0. So when I have exact sequence, I'll just write it for a free bicyclic group. And both these and these have the Euler characteristic defined, so they have finite k pi 1s in this case. Then the Euler characteristic of this middle part is a product. So this is in Brown's group. So you can think of the Euler characteristic of the group as just the Euler characteristic of a k pi 1 for the group. Okay, so these are going to be 0, and then the higher ones are also going to be 0 because of the dimension of the group. Okay, and then by the result that I erase, this is going to help us show that many groups are not QI to free bicyclic groups. Okay. Okay, so another thing that's like this maybe I can use this and see if I can do it correctly. So definition. Okay, I'll put this one first. A group G is residually finite, rationally solvable or refers if there exists, I called it HI. Okay, so I want I'll just erase each one of these. So it's also going to be nested. Okay, I also want the HI to be finite index normal subgroups. And I also want the intersection of the HI to be the identity. Okay, but there's another condition that I want. So this is similar to residually finite. So not all residually finite groups are residually finite rationally solvable. I want the map alpha I that takes HI to the free abelianization. Okay, so the abelianization is just going to give me the first homology of this group with z coefficients, and the free abelianization will give me like the rank. Okay, so what I want with the kernel of alpha I to be contained in HI plus 1. Okay, so what does this condition here mean? Okay, so I'm going to have this map to the free abelianization. And so this will be a cover. So it's kind of like the covers that we took for a fiber. You want to take a cover for some map to Z. So this free abelianization will be some number of copies of Z. So I want to map to Z, and I want the kernel of that map to be in the next level. Okay, so like that cover is contained in the next level. So if I kept taking covers in different directions, this kind of thing will happen. Just give you a little intuition about that. Okay, so, and also by highly non-trivial theorem, due to Agel and Wise, if you have a hyper, it's nested. Normal subgroups, and it terminates in the identity. Yeah, exactly. Yeah, yes. And then I also want this property. So this is a rationally solvable part. That's the free abelianization. I want that kernel to be contained in the next one. The free abelianization, so you map to the abelianization, and then that's a abelian group, and you take like the free part of that. So it's like Z plus Z plus Z plus Z mod 3Z, and it's Z plus Z plus Z is a free abelianization. Oh, okay. So it's the torsion-free part. Exactly, the torsion-free. Yeah, that's a math way to say it. Yeah? Yes, that's right. You kill the torsion. So the free abelianization is you map to the abelianization, which is an abelian group. Abelian groups look like Z to the N plus some torsion. It's Z to the N. The quotients of, okay, so it just says this kernel has to be contained in here. So it doesn't have to actually be the kernel. If it was the kernel, that's nice, but it doesn't actually have to be the kernel. So I don't have to map to, say, Z and then map to Z mod NZ. That's just one example of how this could happen. Yeah? I think it's rational because maybe this is a rank of the rational homology also. So yeah, you kill this, you kill the torsion. Okay. So I'm just going to use that, but it's an interesting property. And this property was defined by Agel in a really seminal paper on virtually fibering hyperbolic three manifolds. Okay, and then I need to say something. So I just said about fibering hyperbolic three manifolds. Let's talk about fibering groups. Okay, definition. So group G, algebraically fibers. If it admits a surjection to Z with finitely generated kernel. Okay, so why is this a good definition? It's because by Stalling's theorem, if G is a three manifold group, then that means that the group actually fibers. It means that the three manifold fibers in this way. It can be written as a surface times I, where the top is glued to the bottom. Okay, so this is not true for general groups. You don't know what the kernel is, but it is finitely generated. We say it algebraically fibers. Okay, and G virtually algebraically fibers. If it admits a surjection to Z if G prime finite index in G, and it is G prime, and G prime admits a surjection to Z with finitely generated kernel. Okay, so by Luke and we know that the Betty numbers behave multiplicatively with finite index covers. If you virtually algebraically fiber, then your first Betty number is 0. I'll write this as this. Okay, so Keelock proved. Okay, let G, and this is after Egel's result that I mentioned, be an infinite finitely generated group, which is virtually refers. Okay, then G is virtually algebraically fibered. If and only if the first Betty number, L2 Betty number of G, can you read that? Okay, if and only if the first Betty number is equal to 0. Okay, so this is a really useful result. It's useful in terms of getting quasi-isometry because we know that the vanishing of the L2 Betty number is a quasi-isometry invariant. And it's also useful in terms of getting incoherence, as I'll try to explain now. Both of which are really geometric group theory things. Okay, so let me try to explain how this is related to, how this relates to incoherence. Okay, so Barry, so these are kind of old results. I don't know the actual date, but much older than the current stuff on L2 homology. So if G has cohomological dimension, so you can think of this as you take a k pi 1 for the group and you look at the dimension of that, less than or equal to 2, the cohomological dimension, if N is a normal subgroup of G, and N finitely presented, so this implies that N is finite index or free. Okay, so this is really strong. Let's think about how this relates to fibrings. So if I have a fibring, so a map from G to Z with a finitely generated kernel, so if G is cohomological dimension 2 and K is finitely generated, then this means that this K, unless K is free, then this is infinitely presented. So this is going to be a witness to incoherence for any group. Okay, so this will mean that K is a witness if it's not free. G is whatever group of cohomological dimension 2, less than or equal to 2. Suppose you have some group like that. Yes. Okay, and yeah, I think so. I don't think I need hyperbolic. I'm only thinking hyperbolic here. So I might have left it out. So I'm gonna put hyperbolic here. No, I don't think I need hyperbolic. All right, let's see. All right, so now also Hillman-Koklakova, I know this is, and I want to mention this just because there was some stuff about 4 manifolds mentioned in one of the lightning talks. If G equals pi 1 of M4, where M4 is aspherical, hyperbolic 4 manifold, then K is finitely presented, implies K is a PD3 group. Okay. All right. So if I have algebraic fibering, plus the Euler characteristic not equal to 0 in this case, this is going to imply that, okay, I'm going to put hyperbolic here. I think I should have written hyperbolic here. I'm only going to use hyperbolic. I just want to be careful. Okay, so if I have, okay, so what's the deal with the Euler characteristic? Okay, so if it's finitely presented, it's a PD3 group, which is the group that has the same homology with all coefficients as a 3-manifold group. Okay, so this for PD3 groups, the Euler characteristic is 0. So that means that if I have a group, and so then I'll have a exact sequence, like 1 goes to like some PD3 group. This is if it's finitely presented, goes to pi 1 of M4, goes to Z, goes to 1. So that would mean that the Euler characteristic of this was 0. Okay, and even just because this is 0. So that means that the pi 1 of M4 is incoherent. Because if it did fiber with fiber PD3 group, then this would have Euler characteristic 0. And if I know that Euler characteristic not 0, which we know in a lot of cases, then this is incoherent. So really showing that if you want to show that all hyperbolic 4 manifolds are incoherent, which is a conjecture, you just need to show that the algebraically fiber. Okay, so this is a really useful condition. Okay. So a corollary to all this. Okay, wait. Oh, aspherical, yeah. Good, yeah, that's important. And I don't think they need hyperbolic here. No, it's that if it fibers, if the kernel of a fibration, K equals the kernel of a fibration. Thank you. Okay, so if I have some short exact sequence like this, where this is K, that's right, then K is a PD3 group, which means some things about it has an Euler characteristic in particular, so I can make this, I know that the Euler characteristic of my M4 would have to be 0, which it's not. Okay, so this is really useful for understanding 4 manifolds. Okay, so, and then I also have this corollary to that result, that if G algebraically fibers, I just added this in while I was talking about this because I think this is really interesting. Cohomological homology of G, dimension of G equals 2, and G is not F2 semi-direct product Z, then G is incoherent. Okay, so let's look for, so remember I asked this question, and people have asked this of me. Let's try to understand where we should look for groups that might be incoherent and coherent, but that are in the same quasi-isometry class. So let's see. Looking for groups. Okay. Yeah? Okay, so let's do hyperbolic too, just to be safe. It's a corollary to this, okay, because it has cohomological dimension 2, and it algebraically fibers. Okay, then this means that by this, it either has to be finite index or free. It's infinite index, so it has to be free. So it has to fit into a normal sequence that looks like 1. The kernel has to be, if it was a coherent group, the kernel would have to be finitely presented, which would mean it'd have to be free because it's not finite index. So this would have to be Fn going to G, going to Z, going to 1. So this is a free bicyclic group if it's coherent. So let's look for groups that are quasi-isometric, but 1 is coherent and 1 is not coherent. So where should you look for these groups, first of all? Okay, so this is going to come back a little bit to searching for G prime. I'm going to want everything to be hyperbolic. G is quasi-isometric to G prime. Okay, and G is coherent, G prime is incoherent. Okay, so this would show, if you found such a thing, which I have not, I'll show you where not to look in just a second, then you would show that incoherence is not a quasi-isometry invariant. So where should you look if you think, a lot of people think this, and so they're like, why don't you look here or there? Okay, so recall, the boundary of G is a quasi-isometry invariant. Okay, so in particular, if we have two groups that are quasi-isometric, they're going to have the same boundary. So let's think about which boundaries might work. Okay, so boundary. Let's think about some simple boundaries that we know. Okay, so if I have boundary S1, okay, I know that these are all virtually isomorphic to surface groups. Okay, so these are all coherent, so don't look there. I have, and also, if we have, say, S2 boundary, it's conjectured that these are all virtually isomorphic to hyperbolic three manifolds, closed hyperbolic three manifolds groups. And three manifolds are also coherent, so don't look there. Okay, and then, so you might think, well, what if we have more complicated boundaries? Those are really simple. One way that you can make a boundary more complicated is you can take two groups and you can amalgamate over Z. And then you're going to have local cut points in the boundary. Okay, so remember Bowditch, I think I said this, I don't know if I wrote it. If there are local cut points, in DG, and G is not equal to S1. So you'll notice that surface groups have boundary S1, and they do split over Z in a lot of ways. Okay, but you can also take a surface group and you can quotient out to get a rigid orbifold group that won't split over Z. So that's this only exceptional case. That's why we have this. There are local cut points in DG, and DG is not equal to S1, so you don't have a circle. Then G splits over a two-ended group. Okay, but if H1, I'll just write this, over Z of H2. So if I take two groups which are coherent and I amalgamate over Z, the result is coherent. Because if I take, like I look at the way that subgroups sit in here, they're going to look like a subgroup of this, subgroup of that, maybe some different conjugates, all connected along subgroups of G. Okay, subgroups of Z, this amalgamating subgroup. Okay, and all the subgroups of Z themselves are finitely generated. Okay, so that's automatically going to give me a finite presentation for any subgroup if both of these are coherent. Okay, so I'm not going to take coherent groups and put them along Z to get incoherent. That will never work. So this is coherent exactly when H1 and H2 are coherent. Okay, so I don't want local cut points. Okay, I might as well just look at boundaries without local cut points because I'm not going to get anything new by amalgamating over Z. Okay. Okay, so what if I had some other boundary? So I want low dimensional mainly because we know about low dimensional boundaries. So there has been some work that was mentioned in the talks where there's been more higher dimensional boundaries found, but most of the boundaries that we know of are low dimensional. So I'm going to argue in a minute that we're going to have to go higher dimensional. Okay, so let's go to more boundaries. Okay, and also if we know that the boundary is planar, so this means embeds in S2. Then unless they contain a Sierpinski carpet, I'll say what a Sierpinski carpet is in a minute. They are, let's say virtually Kleinian, but virtually isomorphic to Kleinian groups. Okay, so this is due to Heisinski and Chris, and I have another proof even for relatively hyperbolic groups. Okay, so what's a Sierpinski carpet? So our Sierpinski carpet is contained in S2, so in particular, this doesn't include the case of S2. Okay, so I want to look at groups whose boundaries okay, let me say one more thing before I say this. So I have a boundary, a Sierpinski carpet, it's also conjectured to be virtually Kleinian. So I don't want any planar boundaries. That was the point of this little talk over here. So unless they contain a Sierpinski carpet, they're known to be virtually Kleinian, which means they're coherent. And if they are Sierpinski carpet or they are S2, that's conjectured to be. Okay, so they're all so don't look there. So we want to look at groups whose boundaries are non-planar. So that means doesn't embed, don't contain a local cut point. And we want to look at them being one-dimensional just because that's all we can deal with, okay? But this is not a good requirement. It's not necessary. I'm just doing it because that's what I know, okay? It's not actually needed. It might be, but there's nothing that we know about it. Okay. Okay, so a Sierpinski carpet, let's see if I have the definition here. Oh, yeah. The Sierpinski carpet. Okay, you've seen this before. I won't draw it, but it's the boundary. This is a bad way to define it. This says how much I like hyperbolic three manifolds. So a Sierpinski carpet is just the boundary of the fundamental group of a hyperbolic three manifold with totally geodesic boundary. Equals hyperbolic three manifold. You can get it by taking out, you can take a homeomorphic copy, you can remove this, and then from this one, these, you'll remove all of these. You keep going. There's better pictures on the web, which you can look up at your phone on your phone during this talk if you want. Okay, you take the limit of these. But important to us is this characterization, topological characterization. Okay, where did I write it? Okay. So it's a metrizable. Okay, so we know that boundaries are metrizable. Topological space, which is compact. Boundaries are compact. Connected, the boundaries of one-ended groups are connected. Locally connected, it's locally connected if it doesn't have any, it doesn't split over Z. No local cut, no local cut points. It is going to be locally connected just because it's a boundary. There's no local cut points because it doesn't split over Z. And last one, this one's planar and one-dimensional. I'll put it up here, one-dimensional. Okay. All right, so this occurs as a boundary. We like all of these things about it, except that it's planar. So the Menger curve is all those exact same words, but it's everywhere non-planar. So the Menger curve. Okay, so notice we have all these things, all these conditions hold for boundaries. So I just need a boundary that's one-dimensional. So that's when the group has cohomological dimension 2. I'll say that in a second. These are all going to hold whenever the group doesn't split over Z, is one-dimensional and has planar boundary. Okay, that's what I'm going to have here. So, boundary of G equals a Sierpinski carpet if cohomological dimension of G equals 2. So this is by a result of Baskina and Mess. Okay, that the dimension of the boundary is 1 less than the dimension of the group, which is exactly what you think about. Think about the free group, dimension 1, the Cantor set dimension 0. Okay, so I'm gonna have boundary of Sierpinski carpet exactly when my group has dimension 2. The boundary is planar. And G does not split over a 200 group. Okay, so there's a lot of possibilities. Now, the Menger curve is exactly like this. All these conditions, same conditions, dimension 1, compact connected, locally connected, no local cut point. All these conditions except the boundary of G is everywhere non-planar. Okay, so this means that there's no open neighborhood of it that embeds in the plane. Okay, so this is stronger than just being non-planar. Okay, but let me give you the little argument that for boundaries, it's not. Okay, so for boundaries of hyperbolic group, non-planar, if I have all those conditions, so for boundaries of hyperbolic groups, that are one-dimensional plus locally connected. So they're piano continuum. Everywhere non-planar. Non-planar implies everywhere non-planar. Let me just give this little, it's just a tiny little argument. It's very nice. Okay, so in this situation, Claytor showed that non-planar implies there exists a non-planar graph embedded in boundary G. So let me just draw that. So I have some non-planar graph. I won't draw K33, but I'm thinking of K33 right there, somewhere in my group. All right, so now I want to show that there can't be some little neighborhood that embeds in the plane. Okay, I want to show that some non-planarity one place implies non-planarity everywhere. Okay, and the reason is because in a hyperbolic group boundary, I can find a loxodromic, okay, where the endpoints are in any two neighborhoods. I can pick any two open neighborhoods. This is Tukia in the theory of convergence groups quite a while ago, is that for a hyperbolic boundary, the loxodromics are dense, and so dense in fact that I can take any two open neighborhoods and I can find a loxodromic whose endpoints go from one to the other. Okay, so what this means for a loxodromic, it has north-south dynamics. So everything outside of this point is going to get sucked in towards this point. Okay, so what's going to happen is that this is going to get consecutively sucked into here. Okay, so that's all. So you can't have a hyperbolic group boundary that's non-planar over here and planar over here. They're very homogeneous. Okay, so that means it's a Menger curve if it's non-planar. Okay, we don't want planar boundaries because we know or conjecture too much about them. We want a non-planar boundary. We want one-dimensional because there's a lot of examples of codimension 2 groups. And we don't want to split over Z, so the Menger curve boundary is what we want. So let's look at some groups with Menger curve boundary. How much time do I have? Actually talking too much about boundaries, okay. Okay, so let me just say a few results about. So Kapovich and Kleiner also proved that boundaries using this machinery, boundaries of hyperbolic free bicyclic groups which do not split over a finite or a two-ended group have Menger curve boundary. Okay, so this is basically just the argument that I just wrote there, that if you're non-planar, then you're everywhere non-planar. And same argument. Okay, so remember about free bicyclic groups, they're coherent. So that's nice. They have Menger curve boundary and they're coherent. Handel. all free bicyclic groups are coherent. Okay, and then, so another fact is that free groups by the same argument, okay, so you have to show they can't be, you just show all those properties that I showed and you get mega curve boundary because they're codimension 2, cohomological dimension 2. So free by free groups, which do not split, over finite or two-ended groups have mega curve boundary. Same argument, I won't go through it. Okay, so we have these groups with mega curve boundary which are coherent, and these groups over mega curve boundary, many of which are incoherent. I'll give you a little argument for that now. Okay, so I have two classes of groups with mega curve boundary, and some are coherent by celebrated result of Bain and Handel, and I'll argue that many of the other ones are not. Okay, so these are groups that look like Fn goes to G, goes to Fm. Okay, like free bicyclic, but instead of Z here, I'm going to put a higher rank free group. Okay, I'm going to change this to M to N because that's how I've it in my notes. I don't want to mess it up. Okay, so we say that Fm by Fn has excessive homology if the rank of H1 of G, where G is a free bicyclic group, just with Z coefficients, is greater, strictly greater than N. Okay, so notice I have, this is going to give me more maps to Z. That's the key point. So I have a bunch of maps to Z because my group already maps to Fn. So I already have an n-dimensional space of maps to Z by abelianizing this. And I want to say if it's bigger than that. Okay, so the theorem and this is joint from Rob Kropholler, is that if, I'll just state it for the free by free group case, if G equals Fm by Fn has excessive homology, then G is incoherent. Okay, so just say like one thing about the BNS invariance of the group. So the main thing you should think about this, realize about this is that if I have an extra map to Z, then I'm incoherent. So that's like being, yeah, so maps to Z are very, very useful. Okay, so the BNS invariance of a group G, let me just very briefly say what these are. So I'm going to, the character sphere is the space of maps to Z is how I think of it. So technically it's this character sphere, which equals H1 of GR. Okay, so this cohomology can be thought of maps to R. I'm really thinking of it as maps to Z. I don't care about the 0 one. And then I'm just going to mod out by equivalence, so I'll get a circle. So if suppose I have a two-dimensional space of maps to Z, I'm going to get this circle here. Okay, and Barry, Norman, and Strabel proved that there's this subset, which is an open subset, very important, an open subset is very similar to the Thurston norm, if you know about that, of this character sphere. Okay, such that if I have a map to Z is contained in the character in this invariant, and its inverse is also contained in this invariant, that implies that the kernel is finitely generated. Okay, so alpha is a map to Z. Okay, so this is really nice. And the main thing that's good about this is the fact that it's open. Okay, so that means that if I have a high-dimensional homology, so if I have like two-dimensional homology, then that'll give me more maps to Z, just because I map to the Abelianization, Z plus Z, I get a two-dimensional space of maps to Z. That if I have one map, I've got another one. If I have one that's finitely generated, there's another, because it's this open subset. That's an important thing. That once your homology gets high enough, you have more maps to Z if you have one. Okay, so we can use this to find a fibering, an extra fibering. So I think I'm going to draw it as a surface. So this theorem also holds for a surface group semi-direct product with Fn. I'm not really going to think about that in terms of incoherence, because the boundary of that is a two-dimensional, because that's a three-dimensional group, and it's very complicated. We don't even understand that boundary. Okay, but this theorem holds for those groups, and it's so much easier to draw. Okay, so here I have, so I'm just thinking of SG semi-direct product with F2 here. Okay, so I can write this as a surface group by Z, which is just a fiber 3-manifold group, and another surface group by Z, okay, amalgamated along that surface group. And if I have, so I have all these maps to Z that come just from the regular map to, I have like S and T. So I have these maps to Z that are indexed by S and T. I have a two-dimensional space here. And if I have another one, I'm going to call gamma the new map to Z. Is not in this space. Okay, so, and that map from the whole space to Z will give me another map from this to Z and from that to Z. So now I have a two-dimensional space of maps to Z from this one and from that one, which is great because I can start to perturb. So I'll perturb them the same way. So I'm going to take a new fiber of each one. So the way to think about this just visually is that this one fibers in more than one way and this one fibers in more than one way. And because that comes from a map of the whole group to Z, I can put those together, okay, and get a new subgroup. So I'm going to look at beta 1, which just equals A alpha restricted to G1. G1 is this first side. I won't go over there and write it. So this is a new one restricted to my first 3-manifold plus alpha S of just restricted to G1. So this is the fibering that you see of the first 3-manifold. Okay, so I've perturbed it just a tiny bit, so I should still be in this open neighborhood. Okay, and my second one is going to be since this new one restricted to G2, plus the second natural one that you see. Okay, so these agree. Okay, so on the overlap they agree. The kernel restricted to the surface is the same, so I can glue those together. So what I have, the group looks like some crazy fiber over here that's different. Some crazy fiber over here that intersect this in an infinitely generated subgroup, and some crazy fiber over here that intersects this in the same infinitely generated subgroup. So I can stick those together. Okay, so the amalgamation of the two kernels is finitely generated subgroup amalgamated over an infinitely generated subgroup. subgroup. And it's a result, as I mentioned last time, of B Neumann finitely generated, amalgamated over infinitely generated is not finitely presented. Okay, so, and you can also use, if you happen to know that your group is cubulated, which we know for sometimes, okay, this is still very hard. It's not known for free by free groups if they're cubulated. In fact, I don't even know of a single hyperbolic cubulated free by free group. That could be my lack of knowledge, but I don't think it's widely known. Okay, so if these are cubulated and hyperbolic, then they'll be reefers, and you can show that you virtually retract on any quasi-convex subgroup, and you can use this to show that you have excessive homology. So I'll just note that if you're cubulated, you have excessive homology. I can explain that afterwards if you want. If Fn by Fm is cubulated and hyperbolic, cubulated and hyperbolic, which is hard, then you have excessive homology. So you're incoherent. Okay, so you're like, okay, great. We have got, you might be like, I'm tired of hearing about that, but you also might be like, great. Here is some groups with Menger curve boundary that are incoherent. Here are some, the free bicyclic groups have Menger curve boundary and they're coherent. So you might wonder if they're quasi-asymmetric. Free by free, incoherent for many cases. Okay, so notice that but they're not quasi-isometric. In fact, it's pretty easy to show. So for remember free bicyclic groups, so usually it's pretty hard to show things are not quasi-isometric, by the way. If they have the same boundary, you have to look at some finer invariance of the boundary, like quasi-symmetric, like I talked about the first day, or quasi-conformal, like was talked about in the talks. Okay, so if you have a free bicyclic group, all the Betty numbers are 0, as I mentioned. Okay, but if I have a free by free group, okay, notice that the Euler characteristic of the free by free group, as I mentioned, okay, so this is a negative, negative. This is going to be positive. In particular, it's not 0. Okay, so my Betty numbers can't add up to 0, whether or not I know this is algebraically fibered or not. Okay, so the sum of the BI's is not equal to 0. Alternating sum of the, yeah. Okay, so these are not. Actually, I think that this will be contained in the second one, but this is just easier way to show it. And in fact, let's see how much time do I have? How much time do I have to have at any time? Oh, I have 6 minutes. And this has been proven in more generality by Kudlinski, Monica Kudlinski, and also Sam Fisher. I think has a stronger version of paper. This is the easy version that tells you something. So we have some QI rigidity. So if I have G prime reefers, remember this is residually finite rationally solvable and hyperbolic. I'll make sure I have all my adjectives. And QI to a free bicyclic group. G is free bicyclic, so let's think. virtually. So let's look at this. I think I can just use things that I've written or things that we know. Okay, so it's Qi to a free bicyclic group. Okay, so that means that the first Betty number, which am I using? This should be G prime of G prime is 0. Okay, so that means because of Keylak, because it's reefers, I'm assuming that. Implies that G prime is virtually algebraically fibered. Okay, and okay, there's one more fact I have to tell you. The kernel is FP2, so this is a homological version of finitely presented, okay, because the second Betty number is 0. So I hadn't mentioned that as a result of Fisher, because B12 of G prime, which is the same as B12 of the free bicyclic group, is equal to 0. So that is a new thing I haven't mentioned. That's known. Okay, and Gersten proved, so this is old, that FP2 in this situation implies finitely presented. When I have a codimensional 2 hyperbolic group. These are old results. Fisher is new and uses current L2 homology stuff. Okay, one more thing. And then Berry, the result I talked about earlier. Remember, it has to be free if it's finitely presented. So Berry implies that the kernel is free. Because remember, it's infinite index, normal. The group is cohomological dimension 2. And so the kernel has to be free. So now I've got this short exact sequence. To my group G prime. So G prime might be a subgroup of G because I just had virtually algebraically fiber. I'll put G double prime algebraically fibers. Okay, so then this goes to Z. Okay, that kernel has to be free. So my G double prime is free bicyclic. Okay, so actually these are very rigid. Free bicyclic groups are very rigid if they're reefers, and we don't know about them all being reefers, but many of them are cubulated, so that's nice. Okay, so so these are rigid. The other groups with Menger curve boundary are also rigid. I haven't mentioned them. They're the boundaries of Bourdon buildings. They're very rigid. So it doesn't seem like the Menger curve is the right place to look. This is not a complete proof. This is just that some groups we know that are incoherent are not quasi-isometric to some we know that are coherent with Menger curve boundary. So probably you have to look at higher dimensional boundaries if such things exist. Okay, and I will end there because I have 39 seconds left.
Questions?
Crystal clear. Cubulated. So I just sort of said a thing here. I didn't really explain it. That, okay, so this is where it was sort of over here, where I was showing that if you have excessive homology, then you're incoherent. So if you're cubulated and hyperbolic, then you're virtually a subgroup of a right-angled Artin group, and you virtually surject onto your quasi-convex subgroups. So you can take a copy of Z that's not one of the fiber directions, like is in one of the, say, free groups, and then virtually, and that'll be quasi-convex, you can virtually surject onto that, and that gives you a new map to Z. So being cubulated is really handy. So it's possible that all free by free groups are cubulated. There are some that are known to be cubulated by work of like Manning and Sagiv and Mahan Ming. So, but not all of them. That would be nice to get more free by free groups that are cubulated. Is it known which free by free groups are hyperbolic? Yeah, they're hyperbolic when everything is a toward. Well, okay, so you have to. It's slightly harder than that. So where's my picture? It was here. You have like you have a whole free subgroups of mapping class groups or maps and out FN. Okay, so wait, I said some free by free groups are known to be cubulated. Did I just say that? That's wrong. Some surface by free groups are known to be cubulated. That was that result. I don't know if free by free groups are cubulated. I don't know about that. Okay, the question was, oh yeah, about when it's hyperbolic. So what you want is so you get a whole free group. So instead of a Z's worth, so in free bicyclic groups, you have one generator and you have all these powers of it. And you can look in like the action integular space and you'll get like a geodesic. So you want that free group to kind of like quasi-isometrically embed in the space of like all the maps. So it's really similar to that, it's just one step up higher. And some people have done work on saying when that happens.
Okay, if there are no more questions, let's thank Genevieve again.